you guys have all this information, correct? We've done a demo in the lab. We started with cesium. What's the energy for cesium? 61.7 kV. And we have the channel number. What's the channel number for cesium?
Ada 331.48.
Then we moved on to cobalt, and there are two peaks, 1170 and 1330. And what was the photoelectric peak channel number for 1170?
573.79.
0.79. And then for 1330?
650.39.
650.39. And then americium is 59. And the channel number?
34.08.
34.08. So from this information we can draw a calibration curve from your known source. So we know the energy because it's a known source, and we know the channel number. Alright, let's begin with the lowest. 3408, and the energy is 59. So you have 1 point. So this is 59, 34.08. Then you have another one at 331. So let's say this is 331. Then you have another point. So this is 661.7 and 331.48. Then we have another point, and this is 1170 with channel number 573. So it'll be 1170, and the channel number is 573. Then you have the last one at 1330, and the channel number being 65039. So this is enough for us to have a calibration curve based on different energies, correct only for the detector that we're using in the lab, and you get the best curve for your experiment, for your specific experiment. Alright, this is based on the time that you have set, 2030. You guys have to decide, and why you're deciding so has to be explained later when we discuss on your lab results. So this is the calibration curve. Now we also test the unknown X sample that has been activated by a neutron activation, and what we know is only the channel number. We don't know the energy, right? And we also had another source. You can use barium, you can use radon, you can use anything. It doesn't matter. In my manual, I say you can validate your curve using barium. You can use whatever other source else than the americium, cobalt, and cesium. Alright, let's say you're using barium or radon 226. Depend whatever that you're using. You know the energy, and then you know that the channel number. So you now go to the channel number. What was the energy for barium earlier? The channel number for barium?
183.27.
183.27. Now go to your Excel curve, go to 183 and identify the energy and check if the energy is correct, so that you can validate the calibration curve that you have plotted. That's number one. Number two, you can have an unknown source that you don't know the energy. Now that you have a calibration curve that has been validated, we want to use this calibration curve to identify an unknown source. So the unknown source, what was the channel number earlier? Mustafa, what is the channel number? You recorded it. What do you think the channel number is? Alright, Alpha, what's the channel number?
210.74.
0.74. So 210 is somewhere here. And then because you have a curve, you can identify the energy. And from the energy, you can identify identify based on the radioisotope table and identify the unknown source. So you have to decide what the source is. So this is basically how you use sodium iodide detector to identify an unknown source. And you have used the detector, you have this calibration curve. But else than that, we also need to know what is the efficiency of the detector. That is in part 1 of your experiment. So you'll check what is the different intensity based on different radioisotope sources. So you're going to plot that and you are going to explain in your report what the efficiency and how the efficiency is affected based on different energy. So that's part 1. Part 2, identifying. Now that you have known, it's known, you know what's the energy. Now you are going to study the properties of your unknown source. Alright. The properties that you want to identify is decay constant and half-life. So how do you do that? You set the experiment, let's say at 10:30 AM. Set the preset time, let's say for 300 seconds. And then you get CPS here, count per second. Alright? And then at 11, you set the measurement again for 300 seconds. And then at 11:30, and then at 12, and then at 12:30. So you get all the measurement done at 30 seconds. But you have to record the count, total count. So it goes down a little bit. Like that. And you can extrapolate that. So this is the beginning of your T1. T1, let's say the count here is at 100. So what is half-life? Half-life is when the total radioactivity or total count reduced to half. So you go to your graph and find 50. And based on the extrapolation, go and find T2. Let's say this is at 2:20 PM. So T2 minus T1 is equivalent to your half-life. And half-life is equivalent to 2 divided by
half-life.
decay constant. And you can identify the decay constant. And this is one method to do it. Or from the unknown source, you know what X is. Go and find what is X. Identify the source and identify the half-life. This is still needed to be done, but this is another method. And then you plug it into the formula, you can get the decay constant. Alright.